Okay, so good morning, everybody. Can you guys hear me? My audio good?
Yeah, it's
Yep.
good.
Okay, great. Thank you. We're going to start a new topic. We're going to talk about AC. We've been talking about DC all semester. I'll tell you the difference and show you the difference between the two. Before we get started, though, I was thinking there's one more thing I want to show you from electromagnetism. Has anyone ever heard of a rail gun? You've ever heard of a rail gun?
Yes.
Yeah.
Yeah.
Okay. Actually, had a chance to build a small working model of a rail gun, and I thought I would talk about that first, and then we'll get into the AC stuff. By the way, I did get my scanner. I got a scanner, a copier slash scanner, so I'm able to scan files to the computer. What that means for you is I can send your test out. I've been trying to get exam 2 to you. I left it up at the school, and I'm not allowed back in to get it, so I got to make up another exam. I didn't know how I was going to deliver it to you, but I got my copier working, so I'm able to put that test together and get it to you. So I'll send out an email link or announcement when I post it, and then you guys, so you know it's there, and then you'll have like a week to work on it. So it's not a big deal at all. But I do want to get that out to you. Let's talk about this rail gun. Now, if you're not familiar with the rail gun, a rail gun is a device. It will accelerate a projectile faster than any known projectile. I mean, faster than any bullet. It doesn't use gunpowder. It uses electromagnetism to move the projectile. And the reason I built one is when I was in college, like you guys do a capstone, I had to do a design project, and it was in physics. And they had me put together a rail gun, and my job was to calculate the friction between the projectile and the rail. So let me just show you basically what I did. I took a battery. But first, I made this stand. I made a stand out of 2x4s. I took two 2x4s, one and attached it to the bottom to make a base so that it was freestanding. So I took a 2x4 and I used it as a support. And I made a base out of the other 2x4 like that. So it would stand up kind of like this. Two 2x4s together like that. And then in the top 2x4, I drilled holes and put two metal rods in there. So I drilled a hole through here, and I put these two metal rods through the holes so they stuck out like this. These are the actual rails I'm referring to. And the rail stuck out a little bit on the back side of this. Now there's actually two of these. If you're looking this way, here's your eyeball, and you're looking this way, what you would see, you see the top of this, which looks like this. But then you see these two rails coming out like this. You see a rail right here and a rail like that. So what I did, I took a battery, a car battery, big car battery, and connected up to the two rails. So basically I had a circuit like that. And this was 12 volts. So what I want to do is I want to draw this kind of as a schematic and just kind of show you how it works. And normally when I do this in class, what I do is I show a video of a rail gun, a Navy rail gun. I think they're on like the third or fourth generation of it. I will show that in class, but I don't think I want to try to show it through this application on Blackboard because I don't think it's going to work right. So what I'm going to do, I'll send you the link I want you to look at after I'm done with the video. And you can go look at this yourself, how it works, the one that the Navy put together. But anyway, let me show you with the diagram how this thing actually works. It's pretty simple. You can actually make one of these if you wanted to, and you'll see that it works just fine. So what you have basically is a battery. Let me draw the two rails first. So you got a rail here. You got a rail here. And then you got a battery. Probably got some kind of a switching mechanism, and then you got a battery right here. You got power. And that's it, really. What happens is when you take, these are metal. So if I take a piece of metal, like a metal pipe or bar, and I drop it on there, this thing will fire off in this direction faster than a bullet. You'll see that if you actually do look at the video link that I send you. So the question is, if I put this on here, what makes it move this way? Why does it move? Well, I'm going to draw the projectile right here. And if you're actually looking at this, draw this out on the piece of paper if you can. And what I want you to do is to use the right-hand rule. We talked about the right-hand rule last class. Use the right-hand rule and find the direction of the flux around the two rails, and then find the direction of the flux around the projectile. See how it works. See if you can do that. The right-hand rule. And just to give you a hint, you got to know the direction of current. So if I close the switch, since this is positive and this is negative, current's going to come this way. And the top rail is going this way. And the projectile is going back to the battery in the bottom rail. So knowing the direction of the current, you should be able to tell me the direction of the flux around each of the rails and then the projectile. I'll give you a second to do that. If I use the right-hand rule in the top one, my thumb goes in the direction of conventional current flow. My fingers, remember the arrow I told you about last time? The arrow represents this is like the north, south of a magnet, north pole, south pole. And if you're looking at that north pole, if this is your eyeball, you're looking down at this, what you would see is the tip right there. Whereas if you're looking at the south pole, you're looking here, the way we'll show that is you'll see an X. So this is coming towards you, towards the camera. This is going away from the camera. So if you keep that in mind, the right hand rule says take your right hand, the thumb goes in the direction of conventional current flow. My finger is like the tip of the arrow, so I'm pointing towards you, and you're seeing the tip. I'm pointing into the board, you will see an X. So I'm going to put my thumb direction of current flow, wrap my fingers around the top conductor. I see that my north poles are here, which means my south poles are here. If I do the bottom conductor, it's just the opposite. Current's going this way, so my fingers are pointing out of the board. So my north pole is here. My south pole is here. So you can already see we got a problem. If you're looking at this, remember what I told you about the magnetic field and current. Current causes magnetism, so they're directly related. If I increase the current, I get a really strong magnetic field. And since the resistance of these are metal pipes or metal rods, and the resistance of these rods are really low. If I have a low resistance, I got a high current, which makes the magnetic field between these two rails really, really, really strong. The first time the Navy experimented with this, the magnetic field was so strong it actually blew the machine apart because of the south poles in between here. They're working against each other. The interesting part though happens, let's see, I guess you can see this green. If you look at the direction of the field around the projectile, you can see why this works. If I do the right hand rule on it, I see that the north poles are actually here. And over here I have my south poles. So if you can see that through the camera, these are green. I'm trying to indicate the south pole associated with this piece, which is free to move. These are bolted down with really big bolts when you look at the video. But this is free to move. And since I have this north pole or this south pole against the south pole, this thing is going to see a a really big force that way. So it's going to move off with a really, really, really high velocity. So this thing has I talked about the military. Obviously, it has military applications. There's some thinkers thinking about using this to launch satellites. So there's a lot of applications for this device, and it's pretty, almost anybody can build. It's pretty simple to build. So what I want you to do is, I'll send you a link later of the one that I use in class. You can YouTube this yourself. Again, it's called a rail gun. I'm not going to ask about this. This is just for your own personal interest. Now, what we talked about last video, we talked about motor action. That is important. I will ask about that. But just kind of doing, because I thought it was kind of neat. So with that, I want to move on. The clock is ticking. So let me move on to what I really want to talk about, which is AC. So all semester, we've been talking about DC. DC. And you probably know that DC stands for direct current. And what does it mean to say I had direct current? Well, what that means is, over time, if I look at the current over time, it does not change in direction, it does not change in magnitude. So if I were to make a graph of that, if I make a graph of current and time, it's pretty boring. It looks like this. It's just a line. So in a direct current circuit, a circuit you have with the battery, the current stays the same, doesn't change in magnitude or amount, doesn't change in direction. We now want to talk about AC. AC. And AC stands for alternating current. Alternating current. The fact that it alternates means that for a certain amount of time it's going to travel in one direction, and then for a certain amount of time it's going to travel in the opposite direction. So it keeps doing that, going one way and then the other. And not only does it change direction, it also changes magnitude. So at some point there's no current, then it reaches a maximum, then it goes back to zero, and then it flips direction and does the same thing. It just keeps repeating over and over again. Before I get into that, I want to go back to our last session when we talked about magnetism. Because there was a video I showed you. I want to review that video. I showed the video, so I'm not going to show it again. But in the video, if you remember the video I showed you, there was a person, they had a magnet and they had a coil. So they had a coil of wire, single loop, and they had a magnet, North Pole, South Pole, and they had hooked up to this meter. And what they did, they took the magnet and then moved it back and forth through that coil. And what you saw on the meter was the needle would move back and forth corresponding to the way that he moved through the coil. So if he moved one way, maybe it would deflect this way. Actually, I think it started in the middle. The zero was in the middle. So it was an ammeter. And as he moved that coil in and out, that meter went back and forth. And what that meant is, when he was going one way, the needle went one way. That meant current was flowing in one direction. And when you pulled it out the other way, it deflected the other way, which meant the current had reversed and went in the other direction. And what he kept doing was moving it in and out, and the needle was going back and forth. Now, what you couldn't see, when he had one coil, it was really hard to see deflection in the needle until he increased the number of turns on the coil. He went from 1 turn to 10 turns. And he moved the magnet through the coil. You were able to see a little bit more deflection. And then he went from 10 turns to 100 turns. And when he went to 100 turns and moved the magnet through the coil, you could really see the deflection on the meter. The point of doing that was to tell you that the current produced by this method is related to the number of coils you move the magnet across, the number of coils cut by the magnetic field. The more coils, the more voltage produced. The more voltage produced, the more the needle is going to deflect. Now this needle was measuring not voltage, it was measuring current. But remember, it takes a voltage to make a current. So as he was moving it back and forth, what you'd have was a voltage that had a polarity. A voltage that had a polarity like this. So the current went one way, and then the polarity switched when he pulled it out. So the current went the other way. And if he stood there and moved that in and out, then what you see is just the current going back and forth. It will alternate back and forth. You can see it. Well, what he was trying to demonstrate in that video was something called Faraday's law. I want to start by talking about that. Faraday's law. And that's pretty important. That's kind of like Ohm's law was important for DC. Faraday's law is important to understand AC. So Faraday's law. And there's an equation to represent this, but I'm more interested in the words. So how does it work? Well, Faraday says if you can induce, or you can create, or you can make a voltage. Now remember, voltage is a separation of charge. If I want to make a voltage, I gotta separate charge, and that's what the battery does. Here's another way to separate charge. If I want to make a voltage, I gotta have a coil or conductor. You take a conductor and we coil it up. So I gotta have a coil or conductor. I gotta have a magnetic field. And I gotta have movement. It's gotta be motion between the coil and the magnetic field. If you take away any one of those, this won't work. So this is kind of cool because this gives us a way of producing electricity without a battery. The problem is what we're going to have is a type of electricity that alternates, and that's not a bad thing. It turns out in the world that we live in today, we actually need two types. We need both AC and DC. And as you'll learn, we need AC when we want to move power from one place to another. The power that comes into your house comes to you in the form of AC. When you get it to where you need it to be, we have a circuitry that converts it from AC to DC. So when you plug your computer, your cell phone, you plug something into the wall, there's a power converter, you call it a charger. It's actually taking the AC and converting it over to DC. So it turns out that both types of current, both AC and DC, are important. But we're going to focus on AC. So Faraday's law, you definitely want to know. Faraday says that you can create or induce a electric current, if I have conductor, magnetic field, and motion. If you didn't get a chance to see that video that I showed last class, you want to definitely do that. Well, this is what I called last time. I called this generator action. We looked at motor action. This is generator action. You can actually generate electricity this way. And let me draw what I had before. Last time we were together. Last time we were together, I'm going to draw this a different way. When we looked at motor action, basically a simple motor, I need some magnets. So I had a couple magnets. Here's a north pole, here's a south pole. Here's a magnetic field. And what we did for motor action, we stuck that coil in the magnetic field. And I showed you that if you put a voltage here, that this thing will actually turn. And what they do is they put a shaft right here. You can put a shaft right there, and you can have this motor spin a certain way. If I reverse the polarity of this, the motor will spin the opposite way. If I have a variable voltage where I can increase and decrease the current, this thing will speed up and slow down. Basically, to make a motor, all I need is a magnetic field, coil, and I can make this thing spin around. So we looked at motor action last time. Now you might wonder, well, how's this going to spin? These wires are going to twist on the end, and they're going to break. They actually put something called slip rings on here so that this thing can spin around. I can show you that real quick. It's pretty simple. If you imagine I had a pipe, maybe a copper pipe, and I cut this part off right there. So I cut the pipe real short. So I got a small piece of copper. If I set it up, like this is my copper, if I set it up, I have a ring of copper. So if I set it up, I got a copper ring. And what they do is they cut that ring in half. So I got two half circles. They're metal conductor half circles. And then what they do is they take one of these and fix to this end of the conductor, the coil, the part that turns, and the bottom, they'll connect it here. So it kind of looks like this. They'll take the top and they'll solder that to this. They'll take the bottom and solder to the other wire. If you're looking at this wire, the wire actually, the edge of the wire is like right here. On the top and right here on the bottom. And then these are really close to each other, but they don't touch. So then what you can do is you can take another piece of metal, take a piece of metal and put right here, take a piece of metal and put right here with a spring on it. I can put a spring here and here, and the spring will actually push down this way and this way on these metal. These are called brushes. Those are brushes. And so now I can connect my battery up like this, and current can flow through this thing, and it can spin 360 degrees. Now, if you don't, I don't really care if you know that. I'm just trying to show. If you wonder, well, how do they connect it up to the battery here? That thing's gonna. This is the way they do it. The real point I want you to see though is this. We talked about motor action in the last video. If you didn't see it or you didn't understand it, I advise you go back and rewatch that on YouTube. I think I posted. If I didn't post it, I will post it. I send the current in here. It creates a magnetic field around the top conductor, the bottom conductor. You got that weak, strong field we talked about last time in the video, and that causes it to spin. But really, what we're doing here, we're putting in electricity, and if I put a shaft over here, I can make this thing spin. If I put a propeller, I can make a fan, I can put a pulley. Basically it's doing work. I get mechanical work out on that end right there. What I'm showing you now is basically this is everything Faraday says we need to generate electricity. Faraday says we need a magnetic field. Well, there it is. We got magnets. He said we need a conductor or coil. Well, here's the coil. We need movement. So if I could figure out a way to spin this around, what I would get out on the other end is electricity. So if I put in electricity, I get out mechanical energy. That's motor action. If I put in mechanical energy, I get out electricity. That's generator action based on Faraday's law. Okay, so what does this voltage look like? The voltage that comes out of the generator, what does it look like? I showed you what DC looks like. Well, it turns out that it looks like this. I'm going to draw it as a graph. This is voltage. And this is time. So this is positive voltage. So anything from 0 up to here is a positive voltage. And this is negative voltage. So the voltage I get out of the generator looks like this. And it just keeps going on and on and on forever. You might recognize this as a sine wave. Man. Sine wave. Hey guys, somebody has their mic open. There's a lot, I think you guys can probably hear each other's background noise. So if you have your mic open, unless you have a question, close your audio down so you don't disturb anybody else. So it produces a waveform like this, a sine wave. So to really understand AC, you gotta remind yourself of how does a sine wave, what does that look like? Mathematically, what does it look like? So I want to remind you of some things that you probably learned in your math class. First of all, notice that, as I said before, if we're looking at voltage at this point, it's 0 volts. It goes up to this part right here. And whatever the value is over there, that's the maximum voltage. And it does the same thing down here. It goes down to 0. So it's 0 here, 0 here. And then it goes down to another maximum right here. So here's another maximum voltage. On the top, that's equivalent to a battery like this, where the positive is here and the negative here. And then down here is equivalent to taking that battery and flipping it around, where the negative and the positive is here. So if I had a voltmeter, and this is the red lead, and this is the black lead of the voltmeter, and I took a battery and put in there like that, all right, I get a voltage reading, right? That's positive, and I took this and flipped it over, the needle would go back the other way. So if I kept flipping that battery back and forth, what you see is the needle going this way and then that way, and this way and then that way, it would alternate back and forth. So it's this alternating voltage that produces alternating current. I can erase the V if I want to, and put an I there. And this represents a current that is alternating. So I want to review the basic sine wave and tell you what you need to know about a sine wave to understand AC. So you got this in your math class at some point when you did this. Either in high school or college, you looked at this stuff already. But let me just remind you, a basic sine wave the height of this sine wave from the high point of the sine wave is called the amplitude. That's the amplitude. And when we get to circuits, that amplitude, we're going to call that the peak value. The peak value or the maximum value. We got the peak or the maximum value. The other thing that's important to know about the sine wave is that, and I'll draw it from this 0. This is not working. I'll draw it from this 0 to this 0, but you really can start at any repeating point. You can start here and here or here and there. I think it's easy to look at where it crosses the time. This is time on this axis. So one of these right here, from this point to this starting point is called a cycle. So cycle. So amplitude, you want to know what that is, and the cycle, you want to know what that is. The amplitude is the highest point or the lowest point. If you go to the lowest point, we even though we know it's a negative value, we usually report it as a positive value. And the cycle is just from one point to another point where it starts to repeat. So this would be one cycle, and this would be another cycle, or from here to here would be one cycle, or I can go from here to here, that's one cycle. Any two repeating points is a cycle. But like I said, it's easier to look at where 0 is to see the cycles. So cycle is important. Let me move these words to the other side. You want to know the meaning of amplitude? And you want to know what a cycle is. And then there's one more. Actually, there's two more, but the time for one cycle, the time. From let's say this point to this point, the time, T-I-M-E, the time for one cycle. I usually show that as a T with these little edges on it like that. That's called the period. The period. The definition of period is the time for one cycle. So period is something you want to understand. You want to know what the word means. The time it takes for this to occur. So if I have time on this axis, and I tell you that this right here is 2 seconds, well, if 2 cycles is 2 seconds, that means that one cycle would be 1 second, so the period would be 1 second. So the time for one cycle is the period, and then the other one is called frequency. And the frequency is the number of cycles I can fit inside of 1 second. So let me show you this a different way. For frequency, how many cycles can fit in 1 second? So the way to show that is I'll just take these 2 lines, and this represents time. From here to here. Let's say that's 1 second in time. Okay, so from there to there is 1 second. Well, if I can fit 1 cycle inside of there like this, I can fit 1 cycle in there. The frequency would be F equals 1 cycle per second. But if I can fit 2 of them in there in 1 second, so maybe I have this and then this, then F would be 2 cycles per second and so forth. Well, a cycle per second, a cycle per second they call that a hertz. I'll spell it out for you. So the green one would be 1 hertz. The purple one would be 2 hertz and so forth. You probably heard kilohertz, megahertz, that kind of stuff.
And so we are currently doing.
Somebody has their mic open. I don't know if I can. I know everybody else can hear that. Let me see if I can close. Okay, I think they closed it. All right. So these terms right here, you want to make sure you understand the meaning of these. And I'll go through it one more time. Oh, am I? Okay. I'll go through it one more time. The amplitude is the peak value. A cycle is from one repeating point to the second repeating point to a second repeating point. The period is the time for one cycle, and frequency is how many cycles can you fit in 1 second. So you want to be familiar with those terms. The other thing you want to be able to do is to make this graph in terms of degrees, radians, or time. It just depends. Sometimes this is in terms of degrees, radians, and time. So if I show a cycle, let's just deal with 1 cycle. This is the voltage or current. So I can have AC voltage or current on that axis. Here I can have degrees, I can have radians, I can have time. We'll do it all 3 ways. If I have degrees, then from this point to this point, you probably remember, that's 360 degrees, which makes this 180 degrees, which makes this 90, and this 45, and this 270. You want to be familiar with these points on the sine wave. 45, 90, 180, 270, 360. You probably remember that from your math class. Notice that the sine wave, if I have it here, it peaks at 90 degrees, positive peak, and peaks at 270, a negative peak. It's 0 at 0, 180, 360, and then it starts to repeat. So you need to be able to do that in terms of degrees, but you also have to do it in terms of radians. And you might want to review what a radian is. Basically, it's a unitless number. It's based on a circle. I won't go into the details of it, but you want to review that. But what you would do if you want to show this in radians, if you go around the circle, which basically that coil is generating this waveform, it's going around the circle. When it goes around one time, it'll generate one of these sine waves. So one time around is equal to 60 degrees, or 2 pi in the radians. I'll write it as rads. From here to here is 2 pi. So if I take 2 pi and I go halfway, I divide it by 2. And what I get is pi. So here is pi radians. If I go from here to here, I got pi radians. If I divide that in half, then 90 degrees is pi over 2. So here's pi, here's half a pi. 1/2 pi, 2/2 pi, 3/2 pi. This will be 3 pi over 2. So you want to know this in terms of degrees. You want to remember this in terms of radians. And the other thing I can have on here is time. A lot of times you'll have time on this axis, and that's really easy. You just read it off. It would be in either seconds, milliseconds, or microseconds, or something like that. So if I have time there, then we're talking about the period. So as I said before, if this was 2 milliseconds, 2 milliseconds, and I would say that the period of this waveform is 2 milliseconds. Now there's a relationship I want you to remember that's important. I'm going to give you 2 equations for today to think about. The first one is this. The frequency is 1 over the period. The frequency is 1 over the period. So given the period of 2 milliseconds, I can figure out the frequency, 1 over 2 milliseconds. Well, 1 over 2, that's 0.5. And milli, I have 1 over a milli, that comes up as a K. This will be 2 kilohertz is the way you write it. 2 kilohertz. So you have to do a calculation like that. So you want to remember this formula. If you have I don't know if you're taking notes now, this is one you want to write down and remember. This is important. So F is equal to 1 over period. Period is equal to 1 over frequency, 1 over F. And then the other one is, you can actually, if I know the angle of the coil in the magnetic field, I can actually determine the value of the voltage for a particular angle. So that turns out to be kind of interesting. Let me give you that equation. So I'm going to give it to you for voltage, but it will also work for current. So let's say we have V here. Now notice the way I wrote that V. I've been writing the V like this. When they show it like that, they mean instantaneous value of V. So I want to write it like that. I don't know what your book does. So this formula, we'll use this next time we get together. V equals VP sine theta, where if I give you this waveform right here, let me clean this up to make it neater. If I give you this waveform, and this is volts, and this is degrees, then if I know, let's say, any of the degrees down here on this axis, I can put it into this equation, and I can figure out the voltage at that particular location in degrees. You can kind of already see it, that you know right here, that's 90 degrees. So that voltage, whatever it is, that would be the peak value. That would be V peak. So the way this would work is this. I would give you the formula, and you would know V peak. You would say V equals 100 sine theta. So you might be given a formula like that. And then what you can do is take that formula, and I say, all right, I want you to look at this at 0 degrees. If you put a 0 in here, you might remember from your math class, the sine of 0 is 0. 0 times 100 would be 0 volts. So at 0, I expect to get 0. At 360, the sine of 360, I expect to get 0. If I said, all right, look at it at 90 degrees, you put a 90 in there. You might remember from your math class that the sine of 90 is a 1, and 1 times 100, that will give me 100 volts. And that's saying that right here at 90 degrees, I get 100. Now, if I come over here to 270, I put a 270 in there, I expect to get a negative 100. So using this equation right here, if I tell you the location of the coil in the magnetic field, you can tell me the voltage you get out at that particular location. That's why they call that the instantaneous voltage. So we'll do some calculations with that. Now, I only got 3 minutes, so I need to talk about, let me put some values on the board, and next time we make the video, which will be, I guess, Monday, I'll define these. I'll pick up here. So the important values we're going to work with as we talk about AC, we already talked about the instantaneous value. I'm just going to say value. There's also the peak value. Let me just write the symbols. So this one, this one, this one, this one, and this one. So this is the peak value. We'll define these next time. This is called the peak to peak value. This one right here is important. That's really important. That's called the RMS value. We'll talk about what that means next time. And this is called the effective value. These two right here are actually the same. RMS and effective are two different names for the same thing. And then the last one down here, if you can see it in the camera, that's called the average value. So what I'm going to do next time I make the video, we'll define these. I'll give you equations for these, and we'll do some calculations with these. Again, the most important one is the RMS and the effective value, and I'll tell you why it's important. So I threw a lot at you. I think when we do some calculations, this will come together and make a little bit more sense. So you want to start looking at the book. I don't know what chapter it is in your book, but start looking at the AC part of it. And remember also, I'm going to send an announcement out with your exam. When I'm going to post the exam, post it and ready, I'll let you know when it's up there. Oh, and I got a couple people asking me about exam retake. I got one or two people that sent me an email or a text. I'll have the grade in for your exam 1 retake. The retake, I'll have those grades in by Sunday. So I grabbed everything from the school that I could and threw it in the box when they kicked us out, and just got to get everything organized and get back on it. So I'm behind on a lot of stuff, but I will get that grade in, and If it's not in by Sunday, for some reason, you don't see a grade for your exam 1 retake, let me know, and then I'll take care of it. But other than that, I think you should be good to go. Anybody have any questions for me before we disconnect? Okay, then you guys have a great rest of the day. Stay safe, and I'll see you same time on Monday.